Hello everyone, my name is Tayyip Ensar Özkaya, and at the 3rd International Eurasian Conference on Science, Engineering and Technology 2021, I will be presenting you my research about neural network modeling of a 4-pole 3 degrees of freedom magnetic levitation system based on NARX architecture. This research was carried out within the Yıldız Technical University in the Laboratory of Magnetic Levitation with the supervision of Dr. Kadir Erkan. If you have any questions, please email me over this address. In this presentation, I will first introduce the topic and motivate it a little bit. Then I will talk about the materials and methods used in this research. Specifically, I will show you the physical system that I'm working with, then the system identification concept in general. Then I will show you the architecture of the NARX RNN, and then I will show you the data which is used to train the RNN, and last but not least, I'm going to show you how I trained the network. Lastly, I'm going to show you the results and discuss the results of this research. System identification is a very core concept of control theory. We need to identify systems in order to control them, to optimize existing controllers, and to generate simulations of these systems. Traditionally, identification is done through mathematical modeling, which requires very deep understanding of the underlying physical relationships. Data-driven methods, on the other hand, are allowing us to learn from data and to build accurate enough models to represent the system dynamics without the need of mathematically defining the systems. In my research, I'm trying to model the dynamics of magnetic levitation systems. Magnetic levitation is basically the balancing of an object in space by counteracting to gravitation through force generated by magnetic field. In this project specifically, I'm working with a 4-pole 3 degrees of freedom levitation system. As you can see here, the 4 independent poles are allowing to move in vertical direction and in the roll and pitch directions of the system. The physical system is shown in this slide. We can see the electromagnets here and here. Then the photoelectric displacement sensors, which are used as feedback signals for the controller, 4 on each edge. Then we have permanent magnets, which are used to strengthen the magnetic field of the electromagnets. And we have the ferromagnetic plane core, which is used as the attractor of these magnetic forces. And then we have, of course, the drivers, which convert voltage to specific currents which are needed to drive or to generate specific magnetic fields. The general idea behind system identification in this research is we want to model the system in such a way that we can predict the output for a specific input. To achieve that, we collect data. We first apply a desired input to the controller, which generates control signals and drives the plant, which controls the plant. Then we get the output of the plant, YP, and we want the network to output the same YP as here. So in the training procedure, we give the same input, the desired YD, we give it to the controller, and simultaneously or offline with collected data, we feed it to the neural network, and then we compare the result of the neural network with the actual result and use that comparison to optimize the parameters of the neural network. During training during the training period, this is what needs to be done, and in the inference it's much easier, of course. We only give the desired input and the neural network predicts the planned output of this system. So the architecture of the neural network is shown in this slide. We can see it is actually a pretty simple feed-forward network. The only difference is we have time delays and we have a feedback loop in this configuration. Everything else is actually pretty straightforward. We have what you can see here is a one hidden layer neural network, but the numbers of hidden layers are also a parameter which needs to be optimized, as well as the number of neurons per hidden layer, and of course the time delays of the input and feedback. And because we have a feedback loop in here, this network becomes a recurrent neural network. That's why we call it the NARX RNN. And by the way, NARX means, of course, nonlinear autoregressive exogenous, and is actually used very much in time series predictions, also in sectors like finance. So these are the parameters that needs to be optimized, and in this slide you can see the data that is collected from the system. We have 4 sets of training data and 1 set of test data. We trained with the training data and evaluated then manually the results with the test data. For the training data we applied 200 Hz randomized signals, then 100, then 50, and then 0.2 Hz signals. Those 3 are completely randomized between specific values, and the 0.2 Hz is a structured pulse with specific periods, and the test case is a little bit something more something that would occur in real use cases. We gave a 0.1 Hertz pulse periodically, and we trained completely with these data. The sample rate is 5 kilohertz, but in order to shorten the training time, we downsampled it by a factor of 10. So these are the training experiments. Every row represents one training experiment with different parameters, hyperparameters, and we can see that the result in the 7th row, the error is the lowest. This error is showing the difference between the actual output of this test set and the predicted output of the neural network, the absolute error. And in this row, or in this experiment, we used 50 time steps feedback time delay, 50 time steps input time delay, and 10 neurons in one single layer, and we trained it 676 iterations. In this slide you can see the output of the trained neural network. The blue graph is the measured signal from the system, and the red graph is the prediction from the neural network. We can see that that the neural network was only able to catch the basic dynamics of the system, and not things like vibration and oscillation. So a use case for this kind of result would be a simulation where vibrations of these amplitudes are not very significant. And that's about it. Thank you very much for your attention. If you have any questions, like I said, you can email me anytime.